So we are looking again at the stereochemistry for the addition of your halogens to your alkene. In the first step of the mechanism is that we get a Romanium ion. So Romanium ion is actually passively charged. And so what happens once you get your Romanium ion, and then you will have your halides, now the other atom of your halogen that bears all the electrons once the heterolysis is done. Okay, you have your bromide here. So it can attack either of the carbon atoms. Okay, so here it can attack this A or it can attack this. Okay, so look at the stereochemistry here. Since you get a hydronium ion here, get your hydronium ion here. So CH3 is directed towards you. CH3 is directed towards you. If we start from our cis butene. Okay, so if we add our bromine in this way, so what happens is a bromine diria, and then you get your stereochemistry. So you can have the same drawing structure. So you have the dash towards you and the broken line H, and then you get your bromine here. And then your CH3, mapush ni siya pababa, no? It will be an SN to attack diri ang dapita. Okay, and then you get your bromine SN to attack here. What you get is CH3 is towards you but pa down. See, hydrogen is away from you but still pa down, and you have your bromine here. And so you look at the stereochemistry of this one. So see, hydrogen is wedged away from you, and you get on this is 1, 2, 3. So this is an R. It's in carbon 2. This one is hydrogen is away from you. So you can see 1, 2, 3 is still an R. And if your bromine you have here will attack letter B, what will happen? So if this, you have your bromine, okay, towards diri A, and bromine will attack diri kang A, bromide rather. If bromide will attack diri kang B, and kani siya maadto diri, no? So if this will attack here, kaning first nga bromine from bromonium ion will get to this carbon 2. Okay, so you look at the stereochemistry, if kani siya ma-attack diri, so you have your wedge directed towards you, broken away from you, and it will be pushed down for an SN to attack. Okay, and this one of course paingon siya diri sa pikas. And since diri man siya nga side kani is na-push siya dito, the same rig happen siya orientation, no? Up diri siya, down diri bromine. Okay, so you have your CH3 towards you and this hydrogen away from you. Diri you have your CH3 towards you and hydrogen away from you, but when this bromide attacks, it will be pushed downward kani. So mahitabo you have your bromine, and then you look at the stereochemistry. This one, this is the hydrogen away from you. So you have 1, priority number 1, and you have 2, 3. So unsa man na 2, 3. This is an S. Can if you look at the stereochemistry here, you get your halogen, your hydrogen away from you. This is 1, priority 1. This is priority 2 and 3. So this is still an S. You get the 2S, DS, and here you get your 2R, 3R. So what happens is that unsa man na si 2R, 3R. You look at here, there is a symmetry. So what you get here, 2R, 3R, and 2S, 3S is an enantiomer. No? So the mirror image of your 2R is actually 2S. The mirror image of this is your 3S. So this one, A and B, are actually enantiomers, are enantiomers. Okay, and once you have that, they actually produce in a semic form if you start from a cis. But if you start from a trans, okay, if you start from a trans, you have your CH3 on the opposite side of the double bond. So you have your bromonium, once it's being placed again, your bromine, once it's being placed near to your alkane, one of the atom will become partially charged. It will be induced, no? The electron density between these two atoms will be induced towards your bromine away from this one. So it bears a partial negative charge and this one partial positive charge. So the electrons again will add to your bromine, electrophilic bromine, and you form a bromonium ion. Okay, so once you form your bromonium ion, what happens is that can either attack this carbon 2 and this carbon 3. So let's say this will attack your carbon, this 2, carbon 2. So pag this will attack this carbon 2 in an SN2 manner, what happens is that there will be a simultaneous bond breaking of this carbon 2. It will go here, and you will actually get your kaninga bromine, no? So the carbon bromine bond will be broken, and the electrons will go paingon diri. So you have 2, 4, 6 ka electrons from 2, 4 na ka 6 ka electrons diri, and you get your bromine diri. So when you look at the stereochemistry, pag drawing ninyo ana sa inyong product, you get a draw the same manner. So you have your CH3 oriented towards you, the hydrogen away from you, you have here. But this is an SN2 attack. Okay? What happens is that kung up na siya, up, away from you but up, towards you but up, there will be backside, there will be a flipping no nga mahitabo, right? Remember your SN2, there will be a concerted backside attack. So ma-flip ang imuhang kani. It will be flipped down kaniya. Now you get yours still this one. What happened here, kaya na naman siya diri nga side, no, wala na may attack. So this, they will attack opposite to your halogen here, katong na electrons, no, to eliminate the electron repulsion from your bromine here. To get this one, what happens is that kani, get your product here. And you get the same stereochemistry, dili na siya ma-outro, your bromine will be here. Kani siya the same gihapon, but you have your bromine, they'll be turned upside down. Okay? Turned upside down, you can sa up mo siyang down, but still the CH3 and the hydrogen is oriented. CH3 oriented towards you, hydrogen oriented towards you. Then let's look at if bromine, the bromide rather, will attack this carbon here. So if this will attack this one here, the carbon bromine here will be broken and it will go here. So the same gap on CH3, hydrogen, kopyahan na nato, no? Here you get this one. And bromine, ubos na siya. Laman na siya hilabtan. And this one, the bromide will not attack diri nga side sa bromine. It will attack opposite aning bromine. Okay? To avoid electrostatic or electron repulsion. So what happens that to attack this one, and it will be a concerted attack. Once it attacks this one, there will be a simultaneous bond breaking, kaning letter B. Okay, there is simultaneous bond breaking. What happens is that ma-flip ni siya. So hydrogen is towards you, CH3 is away from you, up. Pag-attack sa bromine diri, it is a concerted reaction again, and this one will be turned upside down. So pataas na siya, mapaubos na siya. But it's still oriented towards you, and this H3 oriented away from you. Now to check, now we don't know what we get. We have to check on the stereochemistry for each of the chiral carbons. So carbon here is bonded to 4 different group of atoms, and all of them. And you see here this hydrogen, CH3, hydrogen is already away from you. So CH3, this is priority 1, priority 2, priority 3. So you have 1, 2, 3, it's R. And you look at this hydrogen here, hydrogen is oriented towards you, no? So baliktaron naton si atong makuha, right? Kay dapat atong hydrogen, according to our Can and Gall configuration, hydrogen should be away from you and look at the configuration. So anyway, later nato siya baliktaron whatever we get. So priority 1, priority 2, this is R, but baliktad man, this is actually S. Okay, so this is an RS23 dibromo butane. And look at here, this one, kaning sabi. This is hydrogen is already oriented away from you. This is priority number 1, priority number 2, priority number 3. Okay, so this one you have 1, 2, 3 to the left. Okay, counterclockwise. You have your 1, 2, 3. Should have been an S. And this one, let's see. Wait, 1, 2, 3. It should be an S. In this one, let's see, it's away from you. You have 1, or this is done. Let's see. Okay, this is away from you. You have your 1, 2, 3. This should have been an R. I don't know, giun sa niya pag RS diri. So we can look at the configuration of this carbon here. Can get the RS already correct, right? And here what you get actually, supposedly we should get the same RS now for it to be considered a meso compound. So you have your CH3, tama, hydrogen, Br here, and you have your Br, you have your CH3 down, hydrogen here. So if this is hydrogen here, you have CH3 oriented away from you, CH3. So this should be your priority number 1, and this should be your priority number 2, kani. And hydrogen is already away from you. I think I'm viewing it differently, no? So same side. They are on the plane, and here is a dapat mag-view ko dari one. Actually, this is S. The other one, you have your CH3 dito, and then you have your hydrogen here. And this is an R. Okay, I will draw this one sa chem sketch, no, to look at on the stereochemistry of this. But according here, you get your RS. So if anyone can see, can tell me, no, the RS. But I think I'm viewing it differently. The RS, you get actually here from, if you have your trans alkene, you get actually the same RS as your product, and what you get actually is a meso compound, like here, like this one. You have your trans, you get the same 2R and 3S. You have here, and you can actually rotate this one around its axis, you get this one the same. For the other one, for your cis, you get actually a pair of enantiomers. If one is 2R, 3R, the other is 2S, 3S. Okay, so you just have to remember when it's trans, you get a meso compound, and it says, when it's cis rather, you get a pair of enantiomers, and you get a racemic mixture at the end of the reaction. So the only problem is I couldn't get the same RS with this configuration here. I think I'm viewing it differently as if BR here. So I'm viewing it from top. You have your bromine R. This is R. From here. Actually, I'm viewing this as S. I think there is something wrong sa kaning illustration niya. Dapat siguro sa CH3 is wedge siya diri, not broken. Okay, I will review in this kaya sinasayop lang si Solomons, no? Because the way I look at this structure here, basin diri sa illustration diri. Sakto man yung illustration, CH3 is oriented towards you, and hydrogen here, CH3 is away from you. So they are away from the plane. Okay, I will get into this next time. No, I will di na ko makuha ang stereochemistry. It should have been an RS, but I'm viewing this one as S and I'm viewing this one as R. You have number 1, priority 1, priority 2, and you have your H. So it's in the same plane, and you have here, so you have your 1. It's actually an S. Here you have your, it's okay to the I, no? Because when I'm viewing this one, it's actually an SR. Okay ra di ay class, no? Libog din ko. Pero sakto ra, and I understand it now. Atong akong pag-view ka ganina, it's S, and then you have your R. Okay? That's how I view it. Since I view this one as an S and R, and this is a tribromo. This is a 2,3-dibromobutane. So if I start counting this one to be carbon 1, carbon 2, carbon 2 here is S, carbon 3 here is R. Baliktaron ni mo na siya, it's actually just the same, no? Kaya pareha naman siya sa H3. So RS, pareha na siya. So this is actually a meso compound. So I understand it now. Even if SR siya, but since it gets a plane of symmetry, na you can rotate this one. And if you start counting here, if this is our carbon 1 and this is our carbon 2, you actually get the same RS. Okay, so I get it. So you still get your meso compound, because if this is your carbon 1, carbon 2, carbon 3, carbon 4, you will get the same one. If you count this carbon 1, carbon 2, 3, 4, because either way, start from this end or to the other, you will get the same, no, for priority. So this is, if this is S and this is R, and if this is S and this R, okay, we start counting from the right, you still get an RS, the same one as this. So either way, SR, RS, you get the same, and this is actually a meso compound. Nakalimut lang ko. Okay, so the only thing I need to consider pag you have both RR, SS, those are exactly enantiomers. And because there is a plane of symmetry here, even if RS ang kaning view na to ani and SR kaning isa, no, you will get either way, regardless of how you count. If you count starting from here, you will get an RS23 dibromobutane. Okay, so it's either way, SR or RS is still the same because it's a meso. Kinalangan dato, let's go on the other reaction of your alkene, which is the halohydrin formation. So earlier we used a halogen in the reaction, but that kind of reaction actually is made in the presence of an organic solvent. For example, in the presence of, wala indicate me kung ano, but I have to say here, this kind of reaction is in the presence of an organic solvent. In the presence of an organic solvent, let's say e.g. CCl4, or you have CCl3, example lang. So it's actually an organic solvent. E.g. example. Okay, so the other kind of reaction, if we do the halogenation in the presence of water in aqueous solution, what we get actually is not a vicinal dihalide, but what we get is a halohydrin. It's a halohydrin. You get your halogen and you have your OH, okay, hydrin. Okay, so molecule, when halogenation in the nanophilic solvent is carried out in aqueous solution rather than in nanophilic solvent, the major product again is a halohydrin, or also called as your halo alcohol. You have your halogen and your alcohol instead of a vicinal dihalide. So what happens? We'll look at the reaction later. The first step always is the formation of the bromonium ion, or that's halogen ion. That's halogenium. halonium ions. The first step is always the formation of the halonium ions. Okay, you have your halogen, which is positively charged, forming a cyclic ring to your carbocation ion, and once you get that one, you attack your nucleophile. So anyway, what you get here, the major product is a halohydrin, although it's still possible to get minor product, which is a dihalide. But the major product again is you have your halogen and the OH attached to. If you do the halogenation in the presence of water. Okay, so let's look at the mechanism. Again, the first step is the formation of the halonium ion. The, the electrons from the double bond will add to your halogen that bears a partial positive charge, and the other will get the electrons from the bond. Again, your halogens here will have your partial positive end, the other is partial negative end. This is the induced dipole when this halogen is situated near your alkene. No? So this is rich in electron density here, rich in electrons because of the pi electrons. So if makasilingan siya ng halogens, one of the halogens will be induced to be partially positive and the other will become partially negative. So masilingan man siya, all the electron density between the two again will go to your another halogen atom. Okay, so it will add the one to the positive end, the electrophile near halogen, and kaning electrons to form here. And once it forms a bond, the other carbon will be positively charged, right? And to disperse that one, see halogen will attack also that to form your halonium ion here. And once this bond is being formed, there is also concerted bond breaking process between the X and the X, the halogen atoms, no? It's a heterolytic bond cleavage here. So you get your halide ion. Once you get your halide ions, what happens that instead of your halide ions, it is the water that will attack. It's not the halide. And you look at which one will be more nucleophilic. Would water be more nucleophilic than the halide? No, so for example, it's bromine. Bromine has a very high polarizability as compared here. Although they are both nucleophile, they're both electron rich, there will be a competition to the addition to the nucleophilic attack to your carbon. Will it be the oxygen bearing the electrons, or will it be the halogen, the halide, containing the electrons? So what happens in here is that it is the oxygen that will attack your halogen, your carbon here from your halonium ion, the partially positive carbocation here. Okay, so once it attacks this one, you get your protonated halogen. Once it attacks, it forms a bond, will utilize the electrons on the oxygen, form a carbon-oxygen bond, and just carry on the two bonds sa imong hydrogen, and the positive charge is na lang ka electron. So once it attacks that one, kani si carbon X, carbon halogen, the electrons between them will go to your halide, and you get your 2, 4, ika-6 ang ika-aning electrons. Okay? So this is a protonated halohydrin. You get your halohydrin, but si OH here is protonated na extra. Of course, si oxygen, kaya nasobra man iyahang bond, no? Instead of duha lang dapat to be neutral, hindi mo siyang tulo with an electron pair here. So oxygen is group 6, -3, -2, it's positive. Okay? Another chart. So what happens is that we use another molecule of water to deprotonate our protonated halohydrin, and you get your halohydrin as a product, and of course your hydronium ion. You get this one. Okay, so in the end, so the first step is the same again for the addition of the halogen. You get your bromonium ion. The second step is, however, you get your two mechanisms differ. Okay, in the halo, water acts as our nucleophile. Okay, and attacks your carbon, and the three membered ring opens up, and you have your protonated halohydrin kani. So more or less the mechanism is the same, except that in step 2 it is the water that attacks instead of the halide. So this becomes a competing reaction. The water and the halide becomes a competing reactor. So that will give us the question, which one is more nucleophilic? Okay, so the more nucleophilic substance is less basic, and the least nucleophilic is, this one, the water is more nucleophilic to attack the carbons compared to this one. And although they are both Lewis bases, no, so the trend is which one will be more nucleophilic than the other. And of course, you see here that this is negatively charged. This should have been more basic, right? But in terms of nucleophilicity, you have a more electronegative oxygen here, so it can easily attack your carbon here. Let's compare this one. So this oxygen is more electronegative than the halide, can easily attack carbon here. If the alkene is unsymmetrical, okay, the halogen ends up on the carbon atom with a greater number of hydrogen atoms. So remember the Markovnikov's rule, no? Of course, when you have your halonium ions, okay, you will always have to choose which atom will bear, or how do you stabilize your developing carbocation? Okay, so if your bromine will add here, okay, you will get actually your carbocation diarrhea. If your bromine will add here, you'll get your carbocation diarrhea. Again, your carbocation is stabilized by the formation of halonium ion. So imagine if your bromine will be added here, the first electrophile bromine, electrophilic bromine will be added here. Okay, using this will become your passively charged carbon before it forms your halonium ion. So you have your passive carbon here, which is more stabilized by 1, 2, 3. So you get actually a tertiary carbocation. Your bromine, your electrophilic bromine, katong partial positive na bromine will be added here, and this becomes your carbon na partial positive. What happens is that you have only a 1 degree carbocation, which is less stable than the 3-degree carbocation. So what will happen is that we choose adding here the first bromine, the electrophilic bromine will be added here, katong carbon with a higher number of hydrogen atoms. Okay, and then the other one will be added here, the nucleophile. The second step, where it is the addition of the nucleophile, you have here. So you get your OH and Br here. So again, this is for if you get an unsymmetrical alkene. So always go back to the mechanism, what will be your predicted product. And you always have to go to the carbocation, or in the process of the formation of your halonium ion, one of the carbon there will be more stabilized if it is more highly substituted, if it bears a partial positive charge. Okay, so just remember that the halogen ends up with a greater number of hydrogen atoms. So the rich gets richer for bromine. Okay, so the electrophile still attacks to the carbon, which is the electrophilic bromine will still attack the carbon, or will be attached to the carbon bearing more hydrogen. Okay, so this one, write the mechanism. It's a racemic mixture. Write the mechanism. Okay, so if you write the mechanism of this one, similar katong kaganina, no? You get your, okay, so you can write the mechanism for that. 8.16, you get your, of course, you have to follow on the formation of the bromonium ions. Okay, and then, of course, you have your bromine, the nucleophilic bromine, katong bromide, rather, nucleophilic bromide will attack up and down. So you have to propose a mechanism for this. Practice 8.16, when ethane gas is passed into the aqueous solution containing bromine and sodium. What's the question? When ethene, ethene, so your alkene is ethene. And containing, okay, so your alkene is an ethene, and you pass a solution containing bromine and sodium chloride. Okay, so sodium chloride is present only, can have your sodium chloride in the presence of water, right? Can only be soluble in polar solvent, your sodium chloride. So you have to remember this one has to be made under aqueous solution. So the question is, write the mechanism how each of the product is formed. Okay, parihara ani. Kani nga mechanism. But instead of your H2O, no, since you have your salt added, sodium chloride, so it's also possible that you get your chloride. So your nucleophile can be your bromide, your nucleophile can be your water, your nucleophile can be your chloride from your sodium chloride. Once you get your bromonium ion. Okay, so once you get your bromine, Benny? Yeah, bromine. Bromine Br2. So of course, bromine, you don't say dibromide, you say bromine. Once you get your bromonium ion again, you have your bromide, it's your nucleophile for the second step, or water, or you get your chloride from sodium chloride. And you get this. So write the mechanism for that. So have time. So there are compounds in which a carbon has an unshared electron pair and only two bonds. So whenever we have a compound having only two, having an unshared electrons and two bonds, two unshared electrons, about two unshared electrons, or an unshared electrons minimum, and only two bonds. Whenever you get carbon with only two bonds and an electron pair, we call that one as carbenes, or it's a divalent carbon compounds. Duha ra ang iyahang bond nga gina-form. So carbenes are neutral and have no formal charge. Okay, example. This one. Okay, you have your methylene, carbon, duha ka bond, and you have your unshared electron here. Let's look at the formal charge of your carbene here. Carbon is group 4 minus number of bonds, duha. So 4 minus 2 minus 2, duha ka bonds. So group number 4, or valence electron of carbon is 4. To get the formal charge, minus number of bonds, so 4 minus 2, minus number of unshared electrons, so 2 minus 6 is 0. So carbene actually is neutral and have no formal charge. So most carbenes are highly unstable compounds. So that's only the drawback, of course, your carbene is unstable. Of course, we know that carbon should be bonded to 4 atoms, no, or at least contains 4 bonds to follow the octet and to be stable. But carbenes only have 2 bonds, like this one, 2 bonds and unshared electrons. It doesn't follow the octet. We expect this one to be highly unstable compounds. And there is it only exists in a fleeting manner. So soon after you form your carbene, actually they usually react with another molecule. So in other words, carbenes are very, very reactive. The reactions of carbene are especially interesting. We'll know that later because it shows a remarkable degree of stereospecificity. Okay, so although carbenes are extremely unstable compounds, no, to the organic chemist's point of view, they usually like carbenes for reasons that it shows a remarkable stereospecificity. No, they can get a particular organic compound with a very specific, stereospecific compound, and they'll be using carbenes for most of the organic chemists. Okay, the reaction of carbenes are of great synthetic use in preparation of compounds that have 3-membered rings, like here, shown here. Okay, so let's look at the example later. The simplest carbene is the methylene. It's called methylene, and usually prepare that one from diazomethane. You have your diazomethane here, your azo, and your methane, you have your NN. Call this one as a diazo compound. Then you have your NN, triple bond N. So this one is positive, and carbene here, you have here. Carbon here is negatively charged, but overall this is a neutral compound. You call this one as a diazomethane. In the presence of heat and light, you will be able to liberate your methylene and the nitrogen gas. So you have to remember your diazomethane actually, no, since you have your electron pair here adjacent to an atom, which is pi bond, can actually form resonance structures for this. Okay, you get your kani. You form this, you'd like to disperse this charge here, you can get a double bond here. So the electrons, once it forms a bond here, the electrons will go dirty. Or once you have this one, you will get your electrons pabalik diri, and your carbon kani will share this electrons kani di will form its electron diri, and then you have your electrons paingon diri sa nitrogen and CH kaning electrons sa ingon diri. So your flow of R will be here coming to here, here coming to here, and here coming to here. You get your that's H2, that once you have, and then is 2 bonds. Kay even if mag-form mag 3 bonds, no, ang katong isa will be used to form here. Manubra naman siya kung 3 bonds, so it will be used to form an electron pair here, and this one manubra na pod, it will be used to ria. Okay, so you get your 3 resonance structures for your diazomethane. So what happens again once you have the most stable one of the 3 resonance structure is 1. Okay, carbon bears the negative charge, and nitrogen, one of the nitrogen bears the positive charge. Okay, so methylene reacts with alkene. Once you have your methylene, no, it can actually react with our alkene to form your cyclopropane. Okay, so that's the reason why we're talking of the reactions of methylene, because methylene is very reactive to our alkene. Okay, and what we get actually is a cyclic compound. So what happens is that the electrons from your methylene will attack your carbon here, and your double bond will also attack your carbon. You get actually a cyclopropane as the end product between your alkene and your methylene. So another source of another example of our carbenes, you have your Dihalocarbene. So instead of hydrogen, can have your halogen bonded to your carbon. So duha lang ka bond gihapon, carbon bonded to 2 carbon utilizing only 2 bonds or forming 2 bonds with 2 other atoms, but this case the atom is fluorine. Okay, you call this one as Dihalocarbene. Okay, so the same manner that your methylene can be added to your alkene, your dihalocarbenes can also be added to your double bond to form your cyclic compound here. Okay, so here, for instance, the RR here, the alkyl groups are in trans. What you get is, you get your Cl2, ClCl, no? One is the same sides are, the other is the same sides, the other chloride is the same sides are, as you get here. So the addition of CX2 or dihalocarbenes is stereospecific. If the R groups of the alkanes are trans, they will be trans in the cyclopropane product. So trans siya sa atong product pod ng cycloalkene is also trans. The RR is trans, and of course, kanin siya, the Cl is trans to this, the Cl is trans to this one. Okay, both of the halogens. Okay, so we'll just finish our carbene reaction now, carbene reaction before we end our discussion, and we'll continue on. Tomorrow is Wednesday, okay? Dichlorocarbene. So tomorrow, if you go to the university, I will see you in the afternoon. I will also go there, but we can do the lecture online. But if you are present, you can meet me